Okay. Let's just give it 1 to 2 more minutes and then we will get started. Thank you for joining this evening. Okay, I think we should get started as to not delay any further. So thank you everyone for joining this evening. My name is Trisha Satish, and it is my absolute pleasure to welcome you all on behalf of the American Society of Engineers of Indian Origin, or ASEI, and our Southern California chapter, which I have the pleasure of leading as the president. Today marks the beginning of a very special journey, a treat that will continue throughout the year as part of our new monthly lecture series. We're incredibly excited to bring you a deep dive into a topic that blends history, science, and engineering in a truly remarkable way. Before we get started, allow me to introduce someone who honestly does not need an introduction, Dr. Raj Vedam. Dr. Vedam is a scholar, engineer, and author with a truly interdisciplinary background. His work spans applied mathematics, engineering, algorithms, and computer science, and he uniquely applies tools from archaeogenetics, archaeoastronomy, and archaeology to study knowledge systems from ancient India. He is also the co-founder of the think tank Indian History Awareness and Research and has delivered countless thought-provoking lectures that challenge conventional narratives and shed light on India's remarkable intellectual heritage. So tonight we kick off our series Unraveling Ancient India's Engineering Legacy, and over the coming months, Dr. Vedam will take us through a fascinating exploration of the scientific and engineering achievements of ancient Indian civilizations and how these breakthroughs may have influenced global technological progress. His insights promise to be not only informative, but deeply inspiring. Trust me. So just a few housekeeping rules before I hand it off to Dr. Raj Vedam. We will begin with a lecture that'll last about 60 minutes, followed by a 30-minute or however much time we have left Q&A. Myself and Vatsala, who's part of ACI National, will be moderating the chat. And so we're making sure to pick up any questions that are being put down. And we will ask Dr. Raj Vedam those questions once his lecture is over. I kindly ask that everyone stays muted during the duration of this lecture and that there's no disruptions as Dr. Raj Vedam gives his lecture. He'll be sharing his screen, and that you guys enjoy this and take away a lot, and that you come back every month for more. So thank you for joining, and now I'll hand it over to Dr. Raj Vedam.
Thank you. Namaskar to everybody. And thank you, Trisha and ASEI, for inviting me to this series. And I truly hope I don't scare you all away after today's talk. So before I start, there is very somber news from India following what is happening in Kashmir. So I'd like just a couple of moments of silence before we get started. Om Shanti. Thank you. So I'm getting a lot of admit requests, so maybe the host can take over those admit requests. A little bit about me. So I have a PhD in electrical engineering a long time ago, and about 30 years of experience in different fields, aircraft when I was in India, and here in power, electronic design automation, and now in the oil and gas industry. I've worked on so many technologies and things like that, written several papers, patents, and all those kinds of things. Those nice stuff that an engineer generally accumulates along the way. And as far as this space is concerned, I've always been interested in knowing what were the contributions of our ancestors to science and technology, right? If you open any Western book on the history of sciences, typically India is a footnote. And it didn't seem right to me for an old civilization to merely be a footnote in the history of sciences. So many years ago, I started researching on this. And eventually, my methodology turned out to be one of multidisciplinary, evidence-based investigation of Indian history. And it accumulated so many facts regarding our civilization, history, and the growth of knowledge systems that I started giving talks. I've by now given more than 300 talks on different cities in India as well as USA, about 20 or so teacher training workshops. And there are several talks of mine on YouTube that you might like to see at some point if this talk fascinates you. I'm also visiting faculty at Hindu University of America, Rishihud University in Haryana, as well as Arsha Seva Kendram, started by my friend, a Gurukulam in Coimbatore. I'm also on the advisory board of Dharma Civilization Foundation. So that's a little bit about me. So this series is titled Unraveling India's Engineering Legacy. And I hesitate to call them lectures. So I'm going to call them episodes, because that's what it really is. So I'm going to explore ancient math as the starting point over here. And like I said, I hope it won't scare you away with some of these things. And my proposed outline is as follows. I'm not sure it'll be as I've shown. It might change depending on how much material I get or not get towards that. So today we'll talk about math. In the next lecture, I'll talk about, the episode talk about old math and applications. Then we go on to astronomy, then to civil works and technologies, to medicine, to chemistry and other sciences. Then I'll discuss about the dispersal of Indian knowledge systems throughout the world in different time periods, and the decline of IKS also, and the ascendancy of Europe. And we'll talk about modern sciences, modern technologies, and in particular, trace their roots. Where did they start from? We'll do that tracing too. And maybe it'll go beyond this too, but this is what I was able to put together today. So many people are surprised when we say that India had knowledge systems. This is especially so if somebody was schooled in a Western education system. This happens. So we can categorize Indian knowledge systems at a very high level as having philosophical content, things like Shruti and Smriti, encyclopedic content like the Puranas, or humanities contents like Artha Shastra, Nyaya Shastra, or scientific artisan content like math, astronomy, health, agriculture, tech, and all those kind of things. But this kind of a categorization is artificial, because in India, all knowledge systems were seen holistically. Everything impacted everything else. There is no secularization of knowledge systems. So in a sense, all these topics seamlessly they meld into each other. And this is what the evidence shows us. And we have ample evidence of enormous accumulation of knowledge over the years. So at the outset, before I even talk, you might wonder, why this series of talks? Today we have a narrator that says that because of something called Aryan invasion or migration theory, which apparently happened in 1500 BCE, this is when illiterate nomads from Central Asia, illiterate because they didn't have a script, they had an oral tradition, right? So no script, illiterate. So these guys destroyed the superior civilization of Harappa, and India had to wait for 1000 years before civilization returned to Magadha. This is not my line. This is straight from NCERT 11th standard textbook. This is what it says. So they say that after you made contact with the Greeks in Magadha, suddenly in 300 BC, you got the Brahmi script, Ashokan script and all these kind of things, and you became civilized. Overnight, we became civilized, right? And then they say, yours is a young civilization. You have not had enough time to generate knowledge in, let us say, mathematics, in astronomy, in medicine. So if you have this advanced knowledge in these areas, that means you must have learned it from the older civilizations like the Greeks or the Babylonians and so on. So in this cartoonish image, what I've shown is, in this narrative, Aryans brought Sanskrit into India from Central Asia. This Brahmi script evolved from the Aramaic script, a Semitic script that came from Levant into India.
Dr. Vedam, you need to share your...
Am I not sharing?
No.
I don't think so.
Oh my goodness. I've been talking and not sharing. That is terrible. I should have asked that. My apologies. Now can you see my screen?
Yes.
Okay. So you didn't miss much. I just talked about this slide, and we are now on this cartoonish slide over here, where I'm saying that Aryans brought Sanskrit into India. Brahmi was derived from the Semitic script called Aramaic. Math and sciences came from Greece into India, and astronomy, math came from Babylon into India. Turkic Muslims got us culture, cuisine, architecture, music, and civilization. And the British got us science, technology, and rational thought. Even bhakti was taught to us by Saint Thomas, who landed in Muziris. Before that, we didn't have love of the divinity. So what we're seeing is there is a distortion of our identity, as well as all points, anchor points of our chronology, all aspects of our knowledge system, identity, everything has been disrupted here and corrupted. This is what the evidence shows. So this is the background behind which we are talking over here. So if we asked, did India even have knowledge systems as a prelude to this entire lecture series? Yes. Traditionally, our knowledge has been divided into the Shruti literature, that which is heard like an oral tradition, the Vedas, Samhitas, Brahmanas, Aranyakas, Upanishads, and Smriti, that which is remembered, typically a written word. So you see the word and suddenly it makes sense to you as you read it, right? The 6 Vedangas, the Itihasas, texts on Dharma, Artha, Kama, Moksha, Puranas, the Kavyas, Bhashyas, the Nibandhas, and Jain works, Buddhist works, and artisan knowledge systems. So we have a matrix of knowledge systems in India, and anybody could find intellectual expression within the streams that existed in India for a very, very long period of time. The next important question to ask, did we have a formal way of building knowledge? The formality is one of epistemology. Do we have that formal way of learning? And indeed, if you look at the ancient Indian philosophical systems, Nyaya school by Rishi Akshapada Gautama, one-line statements, all knowledge is not intrinsically valid. Knowledge is not valid unless proven. Truth exists whether we human beings know it or not. Very, very profound statements. Yoga, all of us know Ashtanga Yoga, which is codified by Patanjali. Vaisheshika by Rishi Kannada, the basis of our scientific inquiry, which is based on perception and inference. Samkhya, which Rishi Kapila, systematic enumeration and rational examination. Purvamimamsa, Kumarila Bhatta, working on reflection, consideration, profound thought, investigation, discussion. And Vedanta, there are up to 10 schools today, and so on. So, but what we see over here is that India had a well-developed epistemology and mechanisms to build a set of knowledge systems over here. Even today as a scientist, If I want to research something new, I go to the library and I see who are all the people who have worked in this phenomenon that I'm interested in. Maybe I take a journal, an IEEE journal on maybe circuits and systems or whatever, and look at that and say, all right, I make a systematic enumeration of all the facts known in this case through literature survey. I examine their methods, what is the methodology each person used. Then I study the pros and cons, reflection, consideration, profound thought. Maybe I write a computer program, or I go to the lab and devise an experiment, examination, discuss with colleagues over a whiteboard, and suddenly get an aha moment saying, okay, this is what this is all about. So even today, we use the methods of our rishis when we do this study of anything new at all. And India had a word for this. It's called pramana. Pramana was our authority for accepting something as valid. If somebody comes and declares to you that the sun rises in the west, well, that's an assertion and a truth claim. How do you accept it? On what basis and what authority do you accept it? That is pramana, right? So in India, we had pramanas like perception, inference, comparison, analogy, derivation from circumstances, negative proof, shabda pramana, relying on word of experts. Each of these philosophical schools only differed in what was exalted as a valid means for knowledge. That is the only difference between these various sampradayas, you see. Charvakas, for example, they only said my perception and experience matters. They rejected the Veda, Shabda Pramana, all these kind of things. Buddhists said only perception and inference, nothing else. By the time you come to Advaita, it's taking just about everything else. So these are the only minor philosophical differences that we see. And what we also see is India is a civilization that has exalted seeking truth as the goal of life. When you establish this as the goal of life, then the entire civilization has been geared towards understanding reality, what that reality is. Whether that reality is a philosophical reality of Atman and Brahman, or whether it is like Vaisheshika, exploring our natural world and trying to make sense. What is Vidya? What is Avidya? And these kinds of things. And if we talk about the antiquity of the darshanas, even here we can see that, for example, Samkhya, Rishi Kapila is mentioned in the Rig Veda and the Yajur Veda. So we place Samkhya as the oldest along with Rig Veda over there. Vaisheshika, Rishi Kanada mentions Samkhya and he mentions Mimamsa, but he doesn't mention Buddhism. So Rishi Kanada should be placed before Buddhism. Buddha in the Puranic chronology is dated to 1800 BCE. So Rishi Kanada is somewhere before that in Vaisheshika. And Jaimini is before Kanada and probably after Kapila. And Nyaya Sutras were used by Buddhists, so that's also earlier than Buddha. So this is a relative chronology that shows how ancient this tradition of building knowledge in India has been. So this is a brief background for us to understand what I'm doing in this lecture series over here. And Vaisheshika, this is the roots of all scientific inquiry, not only in India, all over the world. It works on perception and inference, pratyaksha and anumana. Perception was seen as of two kinds: external, which we understand by our interaction of the world with our sense objects, and internal by reasoning through the mind. And this is seen as superior to external perception. Anumana or inference was seen as reaching new conclusion and truth from observations and previous truths, applying reason. Is there a better definition for the scientific method? I think this is what it has been, and Indians have been following this for the longest time that we've been doing this. Incidentally, when I talk about how Indian knowledge impacted the world, we learn about how Democritus, a Greek, traveled to India and he has internalized Vaisheshika, and he echoes whatever Rishi Kanada says. He has been echoing that, and he's called the father of modern science. The West loves to exalt Greeks and Babylonians as the founders of things. So the father of modern science. But really Democritus was internalizing Vaisheshika. So civilization. Greeks thought only those who knew the Greek language were civilized. Europeans thought only the white people were civilized, so the white man's burden, civilizing the natives, all this nonsense. Exclusionary religionists who invaded India thought only they were civilized and Indians were not, they had to be saved and all these things. In reality, what we can see is only those who have knowledge are civilized. And in particular, we can say only those who knew mathematics intimately, deeply, in a connected way, they can be said to be civilized. So this is the bias with which we come, that mathematics is at the root of everything at all. It is a language of engineers. If you don't know math, you're an anachronism in the engineering field, right? You simply can't exist without mathematics. And we'll see mathematics is so deeply embedded in the Indian culture. In my next few slides, I hope to show you that. So to set the stage, what I've done here is I've shown you across the arc of time, literally across the arc of time, this civilization has worked on certain concepts repeatedly over and over again, which shows how much of a value they placed on refining certain concepts. In Baudhayana Sutra, for example, the story of pi, he defines pi as 3.114, for example. Then by the time I come to Madhava in Kerala School of Mathematics, he had infinite series for pi, right? But we know it's a rather slow convergence. And by the time we come to Ramanujan in 1910, he had one of the fastest convergent series for pi, yielding 8 decimal places with every term we take. If anybody today says, I've got the trillionth digit of pi and all those kind of things, they are using Ramanujan's formula to do that. So what we're seeing is from Baudhayana's use of pi to construct altars, to Madhava, to Ramanujan, we are seeing 5,000 years of innovation. That is just in one thing, the pi. What about series, arithmetic series and so on? We are seeing Aryabhatta, for example, we can thank him for troubling us through high school days when we had to learn these series. Summation of the first n terms, or the n squared terms, or the n cubed terms. Aryabhatta had formulas for all of these things for applications in astronomy and so on. By the time we come to Ramanujan, he has got convergent values for divergent series. I'll let that digest for a minute. He's got convergent values for divergent series. He's got things like 1 plus 2 plus 3 plus 4 going up to infinity. That converges to value of minus 1 by 12. So don't ask how. You must have the brain of Ramanujan to do this, but he's got a certain metric on the basis of which he does that. But once again, it tells us this civilization has worked on these concepts for so long. One more example, the story of combinatorics. Combinatorics is the root of all of our algorithms in computer science today, right? We can go all the way back to Pingala. Pingala, he enumerates a generation of syllables called Guru and Lagu, right? G and L, as I've shown over here. He enumerates how many syllables there are if you take a word length of 1, word length of 2, word length of 3. And in his expression, we see that binary truth table, for example. And from there, we can go to Acharya Hemachandra Suri, where he was concerned with, if I've got short and long beats, how many ways are there to arrange it if I have n beats to be arranged for, let's say, the chandas and such things in poetry and such things? So his answer was, it should be the n plus 1th number in a series that today we call Fibonacci, but really should be Hemachandra series in that n plus 1th value. By the time we come to Ramanujan, he has a partition function, right? He says, how many ways are there to partition a non-negative integer n? For example, partitions on 4 is 5 because you can partition 4 in these ways. And that is his asymptotic formula for that. So we are once again saying, this is not something that the civilization has taken lightly. This is deeply embedded in the system itself, in the civilization. And we are seeing throughout the applied math process in Indian mathematical history. So we see that Indians observed some phenomena. Then they try to make sense out of it, right? Pratyaksha, Anumana, they try to apply all these kind of things like Rishi Kanada has told us, people like Aryabhatta, Nilakanta Somayaji. Sometimes they understand the physics. Sometimes it's just empirical because they don't understand the physics, only empirical. Either way, they have models for these things and they have mathematics for this. Through observations and measurements of the process, they refine these models with some approximations and parameter estimation. And eventually they use that model for prediction, for tracking. And over time, if they see this model is not good enough, they've gone back and refined these models. So we are seeing a logical, rational approach used by ancient Indian scientists. And I've deliberately used language of engineers today We see identification of a phenomena, modeling its behavior, measuring it, refining the model, approximation of the process, estimation of the parameters, tracking, prediction. All these things, we have evidence in ancient Indian works to doing all of these things. So this is the amazing part of this. And like I said, India has had application-driven historical growth of math. Whether it is enumeration, counting of objects, numerals, arithmetic, addition, subtraction, multiplication, division, this appears in the Rig Veda itself, including the powers of 10 in numbers, we see that. Then we see application in architecture. We see geometry, right angle triangle, circle, pi, square root, and the examples are Baudhayana Sulba Sutras for these things. Application in commerce, in arithmetic, algebra, solving equations, examples are Arthashastra, Bakshali manuscript. Or for the modeling of phenomena like astronomy, we are seeing trigonometry, spherical geometry, approximation, solving equations, Surya Siddhanta, Aryabhatiya. Or very advanced modeling, things like functional approximations, properties, polynomial series, infinite series, solution of equations, algebraic geometry, calculus, combinatorics, and such things in works by Pingala, by Madhava, Yuktibhasha, and other Ramanujam and others. So we are seeing that you name it, you name the area, I will show you where Indians developed novel mathematical methods to address that and continued refining it over time. So where is the evidence? This is all evidence-based series of episodes, right? So in this evidence, we see in Harappa. We know from archaeology that life was pretty standard in Harappa. They had standard weights and measures, whether you're talking about Dholavira, Kalibangan, Harappa, Mohenjo-daro, in any of these places, these were standard, same weights used in a wide geographical area over thousands and thousands of square kilometers. We were using this. And the bricks, everywhere in the 4:2:1 ratio. And the layout of the towns, very, very geometric patterns were seen in these things. Clear evidence of the application of mathematics. And just like today, an engineer is nothing without a scale. So this is the same in Harappa too. We have evidence of the Mohenjo-daro scale, right? So this is a scale, obviously not in centimeters and inches, but the Indians had their own measures for these things. Or in Lothal, we have an ivory scale. Or from Kalibangan, we got a terracotta scale, showing the value that the civilization placed on measurements. If there is measurements, there is a model. If there is a model, there's mathematics. If there's mathematics, there's observation, refinement, and trying to apply it in some sense. All this evidence can be seen in the archaeological record itself. And just like we have archaeology, we also have texts. We have a whole lot of texts in India, oral tradition are transmitted as well as written texts. And there too we see evidence. For example, the Rig Veda, we are seeing in one such verse of multiplication, thrice 7 logs of fuel. So we are seeing 3 times 7. So the notions of multiplication were known. This is what it shows over here. On one more place, it's talking about 360 spokes, but it sets it up with 12 and other 60, 30, these kind of numbers over here. Even division and ratio, for example, says 3/4 of Purusha ascended and the 4th remained in the world, meaning in a sense that division is known, ratios are known, and so on. Even logic like arithmetic logic, subtraction, partitioning, these kinds of things are there. Again, Rig Veda, the Vedas are such that each person has got their own interpretation. So one has got to be careful what we are seeing. But what we are only taking away here is the application of mathematics. We are not concerned with the verse itself, but the fact that there is math here. There is evidence of these operations over here. So numbers, addition, subtraction, multiplication, division, probably used for counting, cosmology in the Rig Veda, for grouping, repetition, comparison, for allocation, Atharva Veda, repetitive cycles in Rig Veda, partitioning of the whole in Rig Veda. So we're seeing in the Vedas itself, these kind of applications are being used. Then, amazingly, in the Yajurveda, we are seeing the powers of 10. We are seeing in the Taittiriya Samhita. Taittiriya Samhita is a text that is attached to the Yajurveda. It is written by the rishi called Yajnavalkya, Taittiriya Samhita. Yajnavalkya, later on when I talk about astronomy, I'll tell you how he can be dated to 3000 BC based upon the astronomy that we see in the Shatapatha Brahmana, which Yajnavalkya wrote. So presumably, these were the kind of numbers they dealt with in ritual offerings and so on. For example, they had numbers like ekam cha, dasham cha, shatam cha, and other such things. So we're seeing every one of these words corresponds to one particular value, 10, 100, 1,000, and so on. So we're seeing powers of 10 here, up to 12. So what do we see here? We are seeing enumerations from 1 to a trillion over here. It is also showing to us implicitly the place value system. The fact that we can represent numbers like this has got a place value. It is showing that. It is showing unique names for large numbers. It is also a precursor to the decimal system itself. So this evidence is there in Yajurveda. What about infinity? Infinity was something that Westerners feared in the 1500s, 1400s and such things, because it was one of those numbers that doesn't conform. They couldn't understand why it doesn't conform and so on. So Atharva Veda, for example, is talking about infinity to every side extended, finite and infinite those around us. Indians knew different kinds, innumerable, innumerable, infinity. In Jain works, 5 types of infinities. Infinity in the real line, in the positive R direction, the negative R direction, infinity this side, infinity that side, or infinity in R2, which is an area, or infinity in R3 as a sphere's radius keeps growing, right? So they saw all these kinds of infinities. Even the Brihadaranyaka Upanishad in the Purnamidam mantra is talking about infinity's properties. That which is infinite, the universe is infinite. The infinite proceeds from the infinite. If you take away infinite, it remains infinite, right? Infinity minus infinity equal to infinity. So we are seeing these kind of notions explode by our ancestors in a very remote past. They were already talking about these concepts. So we are seeing the word for that was Ananta, right? That is what Rig Veda is using, describes space, time, the divine, implying that cosmos is limitless, eternally expanding. That is the kind of ideas seen over here. So we are also seeing Jain philosophers. I already talked to you about them, how they had different kinds of infinities. We talked about that. Texts like Tattvartha Sutra of the Jains, they talked about these kinds of infinities. If you come to the Kerala school in the 14th century, we are dealing with convergence of infinite series. I'll show you that presently. And we see how our ancestors handled infinity with great rigor. Centuries before Cantor, others came on the scene and were talking about these things. So infinity can be seen in philosophical systems like Brahman is infinite, or in Jainism, multiple kinds of infinities, or in Buddhism, infinite causality, or in mathematics itself, infinite series, early calculus, convergent methods, or in cosmology, cyclical, infinite time, universes, an infinite number of universes. We see all these kinds of things over there. So clearly, this aspect of mathematics is also known. So step back over here. Why am I talking math first? Because math is the basis of all science and technology. So I'm going to the root of it to show you evidence in our civilization with mathematics. That's what I'm doing here. So once we build up this knowledge, then we can go on to other areas. So right angle triangles. We know Shatapatha Brahmana, Taittiriya Samhita talk about construction of different altars. For example, the Mahavedi altar, or these kind of altars, or the falcon altar, or the turtle kurma altar, and things like that. All of these things, we simply cannot construct these things if we don't have properties of the right angle triangle. So there is evidence of this from many, many places, but this is the application. And we know the antiquity of this because Shatapatha Brahmana, like I said, can be dated to this time frame. So at least from 5,000 years ago, our ancestors have been doing things of this nature. Then we got a Sri Chakra, or what called the Sri Yantra in the Rig Veda. So it's also there, the Sveteshwara Upanishads or Puranas. It's formed with 9 intersecting isosceles triangles. It encodes various irrational numbers. This is a modern understanding of these things. But then if we take a look, there are 4 upward pointing triangles representing Shiva or Purusha, the masculine principle. 5 downward pointing triangles representing Shakti, the feminine principle over here. And they overlap to form 43 smaller triangles arranged in 5 concentric layers, all emanating from Bindu. This is a central point over here. Many geometric points are there, and they've got some philosophical understandings. But our insight comes from, if you want to construct this for ritual purposes, you must have advanced geometry and great precision to align these triangles without distortion, because Vedic rituals demand this kind of precision. So if you have to construct these triangles and place them correctly, you must have the construction mechanisms in geometry. You must understand that. So today's research has shown that we can do this by solving complex nonlinear equations to place them together. But probably ancient Indian mathematicians knew a specific geometrical construction, symmetry, proportionality to do these kinds of things. This is a fascinating piece of archaeology which came from Kalibangan. Kalibangan is a Indus Valley civilization site from 2600 BC to 1900 BC. It thrived. And in one of the excavations, ASI published this particular imagery where we see this flooring, just like today's modern homes have got tile flooring and such things. On this, the pattern seems to be very strange. So I saw this and said, this is a mathematical pattern. And it turns out to be this entity, which I'm not going to describe. It's a mathematical entity over here. But what is of interest is, this appears in Baudhayana Sulba Sutra. It is how to construct a square using circles alone. This is where Kalibangan is in Rajasthan. So Baudhayana Sulba Sutra says, if you drive a stake to the ground, and in the pivotal point you have a stick or something, and you can easily draw a straight line and you can draw a circle. Circle is the easiest thing to draw, right? Then with this specific way of drawing these intersecting circles, eventually you can draw a square. This is how you draw a perfect square using circles. But look at the 4-clover pattern over here. This pattern is exactly what we see in Kalibangan. So it appears that Kalibangan already has this technology that has been proposed by Baudhayana. How is that possible? The Westerners are saying Baudhayana is 800 BC, 600 BC. They pull it out of a hat, literally. But then we are seeing the mathematics of Baudhayana is in use in Kalibangan way back. So we can start asking questions. What is Baudhayana's time period? Should he really be placed to this kind of a time frame, given the kind of geometry over here? And we have a lot of support for this, even if you take a look at Seidenberg's paper on the origin of mathematics, where he speculates that Indians learn from Babylonians, or did Babylonians learn from Indians, or did both learn from a common source. Over there, the points to be concerned with are Baudhayana's Sulba Sutras and so on. So like I said, the Westerners love to date Baudhayana to all kinds of strange time frames, right? So, for example, Kim Lofker, in her book on mathematics in India, places him to 800 to perhaps, right? Perhaps to 800 to 500 BCE. Pingree, who was a professor in New York in 1981, he says Baudhayana is perhaps written before 500 BCE. So it's very speculative. But then we at least have archaeological support saying that we can date Baudhayana to 2800 BCE, which has got more evidence and support than Western assertions, Wikipedia, and all that nonsense that we have, which corrupt Indian chronology. Square root of 2, we see that in Sulba Sutra as well as in Babylon in 1700 BCE. This is a cuneiform text where we are seeing that what is claimed is that it shows square root of 2. This is in Yale in this time frame. So in Sulba Sutra, we have an algorithm over here. And this algorithm can be shown to be equivalent to successive approximation by averaging. Square root of 2 is approximated as this entity over here. So this can also be got by a subset of solutions of the equations of this form, x squared minus 2y squared equal to 1. So the person who wrote this paper suggests that this person, Amrik Singh, suggests that Baudhayana might have known how to find these solutions in order to do this kind of a method. In Babylon, we find that they have it in a base 60 system. These are modern reconstructions. Nobody knows how they did it. So modern reconstructions are square root of 2 is got by this series over here, which has got nothing to do with the Indian way of doing things. So we see the mathematics are different. So Baudhaina, he was concerned with measurements for the dimensions of bricks and altars. These are various Vedic altars, the Sena, Chitti, Kurma, and other such things, Ratha Chakra. Specifications of altar dimensions, fractional operations, square root, pi, geometric construction. We saw squaring of a circle, converting shapes with equal area, and geometric solution of algebraic problems, a speciality of Baudhaina, that you could solve equations, algebra equations using geometry, using constructions. For example, you could know by the ratio, by the properties, what these ratios are, and solve particular equations. And we are seeing that these alter calculations, they involve solving linear equations, quadratic, simultaneous equations. It opens a question, did ancient Indians, were they aware of all of these things? And the amazing thing is there is evidence to show indeed that is the case. Baudhaina might have used geometric means to solve these things. But then Apastamba, who also wrote a Sulba Sutra, I placed him sometime about 800 years after Baudhaina because his mathematics is more refined. Whereas Baudhaina used geometric proof, Apastamba is giving numeric proof of right angle triples. He is presenting all these triples for the Mahavedi altar. He also presents solutions of quadratic equations. He solved linear simultaneous equations as well as linear indeterminate equations for this altar of this particular form. I'm not going to explain all these things. There's no time for that, but he's able to do these things. So we can see that in the Shrauta Sutra, he's got public Vedic rituals for these purposes. Grihya Sutra has got. So each of these are different sutras. The Sulba Sutra has to do with geometry, altar construction. They deal with all of these methods that we see here. And we go on to Manava, who I placed 100 years later in the Manava Sulba Sutra. He's presenting several right angle triangle triples. He also discovered that square root of certain numbers like 2, square root of 2, square root of 61, they cannot be determined exactly. This is the basis of irrational numbers. This was found by Manava in the Sulba Sutra. Also, he provided triples with fractional slides like 2.5, 6, 6.5, and things of this nature. He used a value of pi that we see over here. And he also had arithmetic method to find the largest square in a circle of a given area. All these are equation-based solutions that we are seeing in this time frame. Katyayana, the last in the series, 1700 BCE, he declared that this particular altar is 1/3 the area of this altar. And for this altar, he also provided the right angle triple in terms of irrational numbers, 5 root 3, 12 root 3, 13 root 3. And he also had a method to combine many squares of length A to a new square. This is a formula that he gave, for example, in verse form, not an equation, but in verse form. He solved equations of this form in addition, and we can show that this is the same as Heron's formula for square root. It is known in India much before Greece. In 100 current era, Heron proposed a formula for square root, and Indians had it much before that itself. Then we come to the 1400 BCE time frame when there's a famous astronomy text called Vedanga Jyotisha. Vedanga Jyotisha was written by the rishi called Lagada. What is of interest for us is that it's got something called rule of 3. He says you can apply this rule of 3 again and again. And what is he trying to say here? This rule of 3 in modern mathematics is A by B is C by X. You know A, B, and C by proportionality. You can compute the unknown X with cross multiplication, right? That is how Indians solved some kind of equations. And to give an example, I said, let a planet, let's say Mars, is moving by delta S units in the sky in, let's say, 2 days' time, 3 days' time. Then the question is, 10 days from now, where will Mars be? That is the question. And what Lagada is saying is, you can apply this formula to the known quantities and apply it again and again till the desired result is obtained. In other words, he's using what engineers call iterative prediction of motion using linear models. It's a linear model, but it is iterative, right? Use an old value to get the new value and so on. So this is what Lagada is doing. You can observe the elements of calculus here. As delta t limit tends to 0, we have the definition of differential itself is over here. And given one example, for example, the moon moves through some nakshatras. They want to find how many days does it take to move through one nakshatra? You can apply this and understand these things. Then we go to 800 BCE. I'm coming down in time. From Rig Veda, I came down to Lagada and others. Now we are at Panini. Panini's grammar, everybody knows, Ashtadhyayi. His works exhibit deep algebraic logic, formal rules, generative structures. All these underlie modern computational linguistics, algebraic logic, formal systems, and so on. Given some examples over here, he had meta rules, and these are like the axioms that we have in a mathematical system. For example, he says, if there's a conflict between two rules, the later rule will apply. Those kind of algorithmic axioms are given over here. He introduces logical hierarchy and how to resolve conflicts of that nature. Very, very similar to conditional precedence. In programming, if you don't put brackets correctly, you may get garbage, right? If you have multiple operators, you have no idea what's happening. So that kind of precedence and hierarchy is what he's given over here. Symbolic representation, using a symbolic shorthand, using meta symbols and markers. This is so similar to our using variables in algebra. And if we use syntax trees in computational linguistics, we use that, right? And even things like CNF diagrams in Boolean logic and all those kind of things. It is comparable to algebraic expressions. So these are generalized rules that produce a variety of forms from a few selected base elements. The expressivity is there, right? So it's a propositional logic, that's what we say. From simple atomic propositions, you can construct an infinite number of forms over here. Use of recursion and generative rules. He used recursive rule systems to generate all the valid word forms in Sanskrit. What is interesting for us is this is 2,800 years before Noam Chomsky. He proposed generative grammar. The Westerners had studied the Panini's methods thoroughly before they adopted much of these systems for themselves. So Panini's work additionally has, in algebraic logic, auxiliary system, the Shiva Sutras, a phonological grid of Sanskrit sounds organized to reduce redundancy. Just like we have ka, ka, ga, ga, nga, cha, cha, ja, jan. All these are by the sounds they produce. Are these sounds coming from the back of the throat? Are they coming from the tongue hitting the jaw? Is coming the tongue hitting the teeth? Lips coming together? He arranged the sounds based upon how they appear, right? It's like a matrix, like an algebraic set used for rule referencing, and also makes Ashtadhyayi compact, efficient. He had binary contextual operations. His rules apply in binary combination, Sandhi rules, for example, we know that. Boolean logic, conditional logic, transformational systems, just like we do in modern algebra automata. All these things we do today is there in Panini's methods. So here's a summary of those things. Generative rules, these are sutras to generate valid words. This is generative grammar. Meta rules, conflict resolution, rule precedence and logic in programming, recursion, rule referencing, recursive functions, meta elements or symbolic elements, technical codes and markers, that's why we use it, like variables and functions, and so on. So this is what we see is today we use systems as if they came in a vacuum, but you should know that these came out of the brilliance of our ancestors a very long time ago. So these things are being used today in these forms. From there I go to Pingala. Already hinted to you about Pingala. Nobody knows his date. Even I have no idea. I put 800 BC with a question mark. He could be much earlier than that. He is known for the work Chanda Shastra. It is foundational contribution to combinatorics. All of our discrete algorithms in computer programming is based upon these things, right? Binary numbers, the Chandas procedure and other such things. He solved combinatorial problems, giving early insights into areas central to math, computer science. I already talked to you about the long syllable and the short syllable and how we generate the binary strings of a given length. For example, for 3, n equal to 3, you have this binary truth table of this form over here. He's also known for this Meru Prasthara over here, a triangular arrangement of numbers, right? You construct this with a simple logic, like for example, start with 1, 1, 1, then this is 1, 2, you add these two, it becomes 2, this is 1. And over here, 2 plus 1 is 3, 2 plus 1 is 3. 3 plus 1 is 4, 3 plus 3 is 6, and so on. So you form this table. But the amazing thing is, once you've expressed this table, it helps you to solve how many metrical patterns there are. In other words, NCR is a combination, right? So we know that if you have the binomial theorem today, for example, we know that a plus b to the power of 0 is 1. A plus b to the power of 1, that is a plus b. That's what you have, coefficients of 1 and 1 over here. A plus b squared is a squared 2ab b squared 1 2 1. So this way we can express the coefficients of the binomial expansion using this Meru triangle over here. He's also known for recursive algorithms, right? He provided recursive rules to generate how many meters are there with a given number of syllables. Very similar to this NCR that we talk about, total combinations of syllable patterns. Methods are algorithmic. It is in sutra form, what today we call pseudocode. That is what this is basically. Combinatorial enumeration. He counted how many metrical patterns can be made from n syllables. If there are n syllables, he declared there are 2 to the power of n combinations. This is the basic principle in enumerative combinatorics. Later on, other scholars extended his ideas, notably Hemachandra. And so this is one example of the various terms, concepts that he introduced, Pingala's terms, and the modern equivalent. We are seeing many things like binary digits, expansion. I don't like to call it Pascal's triangles, Meru's triangle, combinatorial enumeration, Hemachandra sequence, and algorithmic thinking. All this appears in ancient works from ancient India. Then we come to 500 BCE, where we have Jain literature. The Jains did amazing amounts of mathematics in accordance with their philosophies, right? Their thought, religious thought and philosophies. In Jain works, we see the rule of indices. Numbers like 10 to the power of 140, 10 to the power of 150 and higher. These are all named and categorized. We see exponential scaling in space and time measurements. There are things like Sagara, 10 to the power of 7 years, and so on, implying recursive exponential calculation that has got index laws. For example, 10 power a times 10 power b, we know is 10 power a plus b. They did not declare this mathematically, but they were implicitly performing these things based on the sutras that they had. So the theory of indices really comes over here. Combinatorics in Bhagavati Sutra and the Kalpa Sutra, we have Jain philosophers accounting permutations, how many beings, karmic states, categories. We see that infinities and other things coming there. Enumeration of n types being grouped in r possible ways. This is talking about combinatorics. How many possible karmic contributions based on state and bindings, that we are seeing NCR come over here. So Kalpa Sutra, Bhagavati Sutra, we are seeing all of these amazing ideas coming in discrete math over there, including logarithms. We used logarithms before we had calculators, right? We use logarithms in engineering to do these things. Well, Jain thinkers, they showed deep intuition for logarithmic scales, classifying infinities, countable, uncountable, recursive time span. Each is exponentially larger than the last one. They use names for successively growing values without linear jumps. Because they have these hierarchical infinities in various dimensions, this classification is showing logarithmic layering of magnitude. Just like today we have log base 10, log base 2 and other such things, they are also showing this layering, that it is in logarithmic layering. So we are seeing rule of indices, combinatorics, logarithmic thinking. All this is coming in ancient India in 500 BCE itself. We have evidence of these in texts like Bhagavati Sutra, Kalpa Sutra, and so on. Then we are seeing commercial mathematics, commerce, right? This comes in Kautilya's Arthashastra in 322 BC, as well as in Bhakshali manuscript later. We are seeing Kautilya's using precise calculations for taxation, division of labor, penalties, reward, standardized weights and measures to measure these things, length, volume, weight, and such things, how to do interest calculation, financial math, geometry for land measurement, for area calculation, ratio for resource allocation, allocation of rations to troops, distribution of spoils in war, division of revenue, trade and currency math, exchange rates, domestic versus foreign currency. Remember, Mauryan Empire had a lot of international links with the Greeks and with the East, also with the countries over there. So these kinds of things, a profit margin, other such things. So we are seeing all of these things: taxation, finance, land revenue, these things, percentages, proportional reasoning, interest, area computation, profit margins, units, conversion, weights, ratios, averages. All these things, evidence is there in Kautilya's Arthashastra itself. So what I've done to you is, before the Common Era, what was the state of Indian mathematics, which is a precursor to our engineering and technology? I've shown to you all the way from ancient times, oral tradition of Rig Veda. I don't even know how old that is. I'm not even going to tell you about it. But then archaeological finds from 3500 BC onwards, we are seeing application of geometry. We are seeing Baudhayana's works, 2800 BC in Kalibangan. Like this, we are seeing all through from 2800 BC, went to Katyayana, we went to Manava Sulba Sutras. From there, we went to Lagadha in 1400 BC. From Lagadha, we came down to even later time forms like Pingala, like other people, all the way to Jain works, 500 BC and so on, and to Kautilya's works. Now I'd like to tell you, from the year 1 Common Era to 1500 Common Era, what is the state of mathematics like? This was a period of intense turmoil in India, in the polity rather. So we see an evolution of Indian numbers. We have evidence for Indian numbers in Brahmi. Brahmi, these are the numerals that we see. Eventually, Brahmi gave rise to Devanagari. We are seeing with zero, a symbol for zero, appearing in Devanagari numbers. We know that in 711 current era, these things went to the Arabs through Bin Qasim's invasion of Sindh. These Devanagari numbers went through Brahmagupta's works and other works, and they were called Gobar in Western Arabic and Eastern Arabic. These numbers morphed into these forms. From here, diffused into Europe in the 15th century and became these numerals that we are familiar with today. Later on, I'll talk to you about how this person, Adam Rees, he made Indian numerals and arithmetic common in Europe in 1522 when he wrote this book on how to use Indian arithmetic for calculations. Till then, Europe was using Latin numerals and clunky Latin ways of calculating. But after this book was written, Europe started using Indian numerals, as you can see in this abacus, and this Indian numerals in this wood engraving over here. Old as zero, right? We are seeing, for example, some people said Gwalior temple has the oldest zero, 876 current era. Some others said in Kaimar, we have the temple where we see the number 605. That is the oldest zero. But then Oxford University, the library rather, sorry, they dated the Bakshali manuscript, which they have the Bakshali manuscript, and that radiocarbon dating came with the earliest time frame of 224 current era, and in that we have unequivocal representation of a zero. So clearly zero is at least that ancient, the symbol for zero. So what is the Bakshali manuscript? It is found in 1881 in near Peshawar in Pakistan. It is a birch bark document, 70 leaves, 36 in fair condition, Sharada script. Now the persons who got that, they were so upset with the mathematics in it that they intentionally disordered them, and they gave it to this person, Rudolf Hornell, for translation. Rudolf Hornell had translated other works too earlier than that, Sanskrit works. So he said he got it in a disordered state, but then he put it in order in great difficulty, did a partial translation, and he said the 2nd century date. He handed it to the Bodleian Library in 1902. Eurocentric mathematician Kay, he got it in 1912. He wanted to disprove Rudolf Hornell's date and show Greek indebtedness. He translated this in 1927 and set a date of 12th century for Bakshali manuscript. He was criticized by Datta in 1929, including Iyengar in 1939, and they said it's got to belong to the early centuries, current era, common era. Pingree revived this debate in 1981. Sushma did a PhD in 1991. One of the best PhDs is a Japanese one in 1995. And this carbon dating in Bodleian in 2017 came with a date of 220 current era. Why am I telling you these things? To show you what is inside the Bakshali manuscript. Today we know these are the numbers shown over here. 0 is very much inside the Bakshali manuscript. And it shows, for example, this fraction multiplied by this fraction to produce this long ratio over here. So these things are, for example, shown in Bakshali manuscript. And Bakshali manuscript also has a formula for square root, which is different from the Heron formula. So I coded these two things in MATLAB. And what you see over here is the Bakshali manuscript, which I start with a value of this one, 390, 625, with a guess. I want the square root of this number. I guess it at 1. It converges in 7 iterations to the actual value, 625. Heron's formula converges in 13 iterations. Heron's formula is known to be quadratic. It's like a Newton method. It's quadratic. Whereas the Bakshali manuscript formula is quartic. Quartic is twice as fast as quadratic. And the evidence I've coded it to try to see for the same values. This is the kind of behavior we get. What does it contain? It contains a square root, like I told you, formula for that. Fundamental operations, addition, subtraction with negative quantities, reduction, fraction, multiplication, division, a root approximation. This method of regular falsi method is over there. Rule of inversion, rule of 3, what I showed you in Vedanga Jyotisha. Proportional formula, partial addition, subtraction, simple equations with one unknown, multiple unknowns, indeterminate equations, and arithmetic progressions, commas. These are the, and problems for travelers, rules of problems for travelers. Examples of equations, simple equations and one unknown. Linear equations with more than one unknown. Quadratic equations. Linear equations with 5 variables. Indeterminate systems of equations where you have fewer equations, more variables. These are the kind of equations that Bakshali manuscript has. And Bakshali manuscript says it was written by a Pandit. He was commissioned by a Vaishya person, merchant, to teach his son about these kind of mathematics. And he says, I did not invent any of these things. I merely cataloged all the methods known to me. So that is what we see here. I claim that Bakshali manuscript also has a roots of linear programming. Today we have a tendency to think of linear programming as something that came from Danzig, George Danzig, and people like that. But there's a problem given in Bakshali manuscript that I can pose in this form that can be posed as a maximization of C transpose X such that AX equal to B. Very, very similar to our linear programming. I can cast it with this form. And the answers that Bakshali manuscript proposes says that it understands some properties of linear programming at least. So it's amazing to see the roots of LP itself goes back to this time frame. Okay, so what I've done for you is I've made a very quick traversal from very, very ancient times. And I said, let me talk to you from the year 1 to the year 1500. But I did not go up to 1500 because I want to save some for the next episode also, 1 month from now. So instead, what I've done is I've curated a few things to show you some selected contributions of Indians to mathematics. I'm not going to show you the applications itself today. That'll come in a later time. Everybody knows about 0, right? That's what people say. Indians gave 0. That's about it. A symbol for 0. Well, we know that Brahmagupta, he formally used this. But 0 is known even in Bakshali manuscript in 220 current era. It's also known in ancient Indian mathematics. There were dot, for example, that was used to represent a 0, such things. But then formal use and rules for arithmetic operation with 0, Brahmagupta did that. 0 as Shunya is known in Vedic literature itself as a symbol, at least from Bakshali manuscript, we know these things. Decimal place value system. So we know that at least from the time of the Vedas, the Rig Veda has gotten very intriguing number. This number is 3339. And this number is represented the way it appears in this particular Rig Vedic verse. It's Trini Shata, Trini Sahasrani, Agnim, and these things. And over here you see Nava and so on. So we're seeing 3,339 divinities have worshipped Agni. The way it is written implies place value. 3,000s, 300s, 30 and 9, right? So clear understanding of place values there in the Rig Vedic system itself. It is not something that Aryabhatta got much later, as the Westerners like to say it, but evidence of this is there in earlier literature itself. It was formalized in the Gupta time period, but I put a question mark on that. It could have been even earlier than that. So the base 10 propositional system is seen over here. The position of the digits determines the value. That is what we see in the way these numbers are presented over here. Numerals, I've already told you the evolution of numerals, how from Brahmi we are seeing in evolution in Devanagari kind of system, going on to Western Arabic, going to Eastern Arabic, going on to 15th century and to the 16th century, and coming with as a present day numbers. So the roots of these things go back to Brahmi and go back to the ancient Indian evolutions. Negative numbers, these were a big innovation. We see it in Bakshali manuscript itself. We are seeing operations with that. But Brahmagupta, he codified these things. He tried to give rules for that, right? How to operate positive, negative numbers. He referred to that as positive is a fortune and negative is a debt. So he says when zero is added to a number or subtracted, what should we do? Number remains unchanged. A number multiplied by zero becomes zero. He says a debt minus zero is a debt. Fortune minus zero is a fortune. Zero minus zero is zero. Debt subtracted from zero is a fortune. So these are all things that we learned in high school, right? So these are the kind of things that Brahmagupta in the 6th, 7th century, he presented some of these things in his work, Brahmasputa Siddhanta and other works. Rules for arithmetic operation already showed to you how the Vedas itself deal with basic operations, multiplication, division. We are seeing that the Vedas, we are seeing that Sulba Sutra, Vedanga Jyotisha, systematic methods to do addition, subtraction, multiplication, division. These were taught in schools from early times, from oral tradition. People had oral means to doing these kind of mathematics, including written down. Even on, they would write on dust. That's why the Arabs called gobar. Gobar means dust, because Indians wrote on chalk dust, or sand, sawdust, and things like that. So these are the kind of ways Indians were teaching these things to. One more of the things I've curated is Kutaka method. Kutaka method is called pulverizer, right? This is an algorithm to find all the integer solutions to indeterminate equations, meaning fewer equations, more unknowns. What is amazing here is you're finding integer solutions, not just one solution, all the solutions, right? That is what the Kutaka method does. It is a precursor to Euclid's algorithm to find the greatest common divisor. Also, later on, the Westerners attributed somebody called Diophantine as a person who did this, which is bogus. This comes from Aryabhatta's method. So we are seeing, for example, if you have to solve these two sets of equations, you're seeing three unknowns, x, y, and z, but we only have two equations here, right? So using Kutaka method, which I have not shown to you, the general solution comes out to be parametrized. It is parametrized on t. X is got as 1 minus 7t, y is 1 plus 3t, z is 2 plus 5t. When t is 0, we get one particular solution, 1, 1, 2, that satisfies these two equations. Then when t equal to 1, you'll get one more solution, t equal to 2, t equal to 3. You can go on till infinity if you like. And every one of those solutions will be solutions to this equation. This is the amazing thing in Aryabhatta's work. Indians worked with algebraic equations long before the rest of the world even could deal with this. Remember, the West worked with Latin numerals. They worked with geometry. The height of the Greek civilization was Thales' theorem. Thales' theorem was geometric construction with similar triangles and proportionalities. They solved equations with geometric means. How Baudhayana used to do it in 2800 BCE, that method went to Babylon. From Babylon, it went to Greece. And that's how the Greeks were doing it, right? But then we're seeing Indians have refined it from the time of Manava Sulba Sutra itself. They have gone away to algebraic equations. We are seeing solutions of linear, quadratic, cubic, indeterminate equations. Brahmagupta, Bhaskara II, they provided general solutions. I've given one particular equation over here, x squared minus ny squared equal to k. This is something that today is called Pell's equation. The Westerners called it Pell's equation. but they had no clue how to solve it. Euler and the others tried to solve it. More than 100 years the West tried before they were able to get a general solution. But 1000 years earlier, Brahmagupta had given not only a particular solution, he had the general solution using the Kutuka algorithm. He had got that. And the method is, for example, this Chakravala method, cyclic method, where they use a Brahmagupta identity. If you have two particular solutions, x1, y1, x2, y2 to these equations, then this is also a new solution. This product terms that you see, this is also a new solution to this. So by trial and error, you get some approximate solutions, then you generate better and approximate solutions and keep cycling till you get the result that you want. And that is a minimal solution when k equal to 1. So these are the kind of things that Indians were doing. These are not mathematics for the sake of mathematics, but these had applications. It had applications in altars, it had applications in various other things. I already talked to you about the Meru triangle, how it is used in prosody, a combinatorial arrangement. 2000 years later, the Westerners, they call this Pascal's triangle, right? But it is really the Meru triangle. And already talked to you about how we can use the coefficients from here for the binomial theorem. Permutations and combinations, already talked to you about Pingala, Bhaskara, how they have detailed works in this, in addition to Pingala, works the Bhaskara too, in poetic meters. So we are seeing permutations that were called as Vikalpa and such things. Bhaskara and Leelavati, which is written around 1150 current era, is exploring how many ways things can be arranged. Leelavati is a mathematical textbook that he wrote apparently for his daughter or for his favorite female student, right? So over there, he's saying how many ways can 3 different letters be arranged? He's showing factorial 3. Then he's giving the rule in verse and word problems with ornaments, with people, with letters, combinations. For example, from 6 flowers, how many ways can 2 be selected? Or partitioning grouping. If 5 mangoes are to be distributed with 3 boys, in how many ways can it be done so that each boy gets at least 1 mango? So the kind of reasoning here is similar to what we do today in integer partition theory. Partition theory is critically important, right? Today in many, many applications. So here we are seeing the roots of that go back to this early time frame itself. Use of symbolism. So symbolism is something that people attributed to René Descartes and others. They said our modern coordinate geometry and our modern XYZ for unknowns that has come from René Descartes and other such people. But we are saying symbolism is ancient in India. We are seeing symbolisms, for example, letters and symbols to represent unknown is a precursor to symbolic algebra. We know that Aryabhatta, he had this alphanumeric system, where you can see this, these are the vowels over here with 10 power 0, 10 power 2, 10 power 4 and so on. And the consonants ka, ka, ga, ga, nga over here with numbers 1, 2, 3, 4, 5. So by using these over here, he could versify mathematical constants and formulas. A similar kind of thing was done by Madhava in 1300s, the Kattapayadi system. So in the Kattapayadi system, what we are seeing here is these consonants, ka, ka, ga, ga, nga, cha, cha, ja, janna. So 10, right, from 1 to 0. Then again, ta, ta, da, da, na to here, and these numerals over here. So using these, he could versify, for example, the value of sine, the sine tables, all those things were made into verses that could easily be remembered, right? Mnemonics. You don't have to carry your reference book with you all the time. You can just remember this mnemonic and you could do these kinds of things. Then Brahmagupta, Bhaskara too, they refer to the unknown quantity as yavat tavat. Literally it means as much as so much. It's a placeholder for an unknown. Similar to today we say let the unknown be X. Like that they used to do this kind of a thing. They did not say let it be the X and so on. So we are seeing that they didn't use symbols, but they had a placeholder concept, systematic terms or operations, structured syntax. These are all conceptually similar to symbolic algebra. These ideas of Indians, Brahmagupta's works, Aryabhatta's works, Bhaskara's works, all these were transmitted to the Islamic world through Persian translations and diffused to Europe. And that influenced development of symbolic algebra in the 18th, 19th, 20th centuries and so on. So we are seeing from an ancient period of time through over here. Trigonometry, right? So we are seeing that Indians called trigonometry Jya and Koja, which through some weird translations from Arabic to Latin became sine and cosine. We are seeing these quantities appear in Surya Siddhanta. The version of Surya Siddhanta can be dated to 600 BCE because of the astronomical naming of nakshatras, we know that is 600 BCE. Also, Aryabhatta in 5th century current era, he also presents these things, both the basic concepts and trigonometric tables. So if we compare trigonometry of Indians and Greeks, world of difference. Although Western historians of mathematics love to say Hipparchus is the father of trigonometry and Aryabhatta learnt his trigonometry from the Greeks. This is what they claim. But the facts show that it is in Surya Siddhanta that sine and cosine appear. Whereas the Greeks only had a chord table. A chord is not trigonometry. A chord is simply that, and you draw a circle, in an arc you draw a line, that is a chord. But then Indians had right angle triangles. Right angle triangles is trigonometry. That is only there in the Indian works. So the divided angle to 360 degrees in 3.75 degree segments, and Ptolemy in 0.5 degree segments, he did this. The radius Indians used was 3,437.5 units, whereas the Ptolemy used 60 units in base 60 system. Indians used it for astronomical calculations, epicycles, planetary positions, and so on, which the Greeks also used for similar purposes. Indians had sine tables, whereas the Greeks had chord tables. And the computation method was recursive sign differences, interpolation. I'll show you these things. Whereas the Greeks, they did not have numbers, they did not have place value, they did not have decimal points. There is no way on earth they could have done any of these things. They had geometric constructions of chord tables, where they're estimating these things, trigonometric entities through geometry. So algebraic framework was used, but they had geometric framework over here. And Indian works influenced Islamic astronomy and later European trigonometry and such things, similarly the Greek. Coming to trigonometric tables, I curated this also as a fascinating thing by ancient Indians. We are seeing trigonometry tables with very high precision in Surya Siddhanta itself, used by Aryabhatta, Bhaskara, Kerala School of Math. All of them have refined these things. In the Surya Siddhanta, we are seeing with a radius of 3,437.75. Where did that come from? That came from 2 pi r is 360 degrees, which is 21,600 minutes over here. Minutes, yes. And so r comes to be this one divided by 2 pi. It comes to this quantity. So the Indian adoption of r is very scientific, very deep in geometry. So with that, it says in Surya Siddhanta, the 8th part of the minutes of a sine is the first sine. 8th part comes out to be 225. That's the first number over here for 3 degrees 45 minutes. And then they have a recursive formula that gives them additional sine values in the table. What is the recursive formula? In the Surya Siddhanta, we can infer these things. With this r radius, theta's angle in degrees, this Jn is a sine value at angle n times delta theta. Delta theta is the increment. Aryabhatta used 3.75 degrees. You start with the first sine value that is given over here. Then the recurrence relationship is the new value of sine is the old value of sine plus this quantity squared divided by del square. Del square really is the second difference. Is a difference formula, Jn minus 1, previous value. So we are seeing finite differences. Long before it appeared anywhere else in the world, we are seeing finite differences in Surya Siddhanta, 600 BCE work. You're seeing in Aryabhatta's work, in Brahmagupta's works, Bhaskara's works. Much later, polynomial approximation, finite differences came in Europe in the 18th and 19th centuries. Even before calculus, Indians were approximating derivatives using these recurrence relationships. Amazing mathematics. By now you'd have goosebumps through your body, right? Because Indians were working with functions and functional approximations. We are seeing functions like secant, cosecant, functional approximation. For example, Bhaskara the first 650 current era, he had this analytic expression, rational expression for sin x. Instead of using sin x, he had this in his mathematical formulas. He was using this. Between this first quadrant, you can use this value. You can see the approximation in MATLAB or any other tool and see how very accurate this is. We also know that Aryabhatta used linear interpolation. Why did they use interpolation? For inverse sine. Given the sine, you want to find theta. If you want to find theta, you must have sine inverse theta. How do you do that? How do you do that? You do that with interpolation. So you do that. Aryabhatta did linear interpolation like I've shown over here. For Bhaskara, for Brahmagupta, first order interpolation was not good enough. That accuracy was not good enough for him to map the astronomical bodies. So he went with second order interpolation. We see that this t squared term coming in over here to compute inverse sine values. And by the time you come to Madhava and Kerala School of Mathematics in the 1300s, he has got infinite series expansion for sine. Sine, cos, tan inverse are these infinite series. 200 years after Madhava, Newton and Leibniz come on the scene, and unfortunately the West calls us Newton series and Gregory series and all these things, but really it is Madhava series. Madhava is the one who got all these terms. So this is an amazing thing about Indian works, that they even worked with functional approximation, error estimation, which is the foundation of computational calculus. Even that was done by ancient Indians that are shown over here. Madhava, he had discovered series of pi, sin x, cosine x, tan inverse x centuries before Newton, and he describes recursive rules to successively calculate terms using previous ones, essentially encoding what today we call Taylor series, these kinds of things. Madhava had got his own series for all of these things to do these computations, showing what a great value Indians placed on accuracy. Why was it not good enough to use the sine tables of Aryabhatta with 3.75 degrees? Why did Madhava have to go to this infinite series? Why did Brahmagupta have to go to second order series? These are the questions you and I need to ask, right? Nobody else will ask it for us. That is because Indians place great value on accuracy. They found earlier novel approximations to phenomena of astronomy in the skies were not accurate enough. So in their quest for accuracy, they do what engineers today do. Engineers today use models that are approximations of reality. If those models don't work in real life, then they go about trying to see, why did it not work? Have I neglected some terms? Is there a frictional term? Is there a nonlinear term I missed out? So they try to model it, say there's an additional term, use measurements, try to make it better. We are seeing evidence of that in India. We are seeing evidence of modeling, using it for some purpose. That model is not good enough. Then we are seeing people coming with novel approximations, Brahmagupta, second order interpolation, Madhava, infinite series approximation, and using it for better and better accuracy. This is what you're seeing, a civilization that is placing great value on accuracy and on reality, truth. This is what we're seeing. Calculus, concepts of limit, calculus, Kerala school developed these things with limits, differentiation, integration. Even to accelerate the convergence of the pi series, Madhava had this correction term. This correction term, today they call it Euler's acceleration, but this is really Madhava's. So we already saw the infinite series. Rational approximation for functions. Correction terms like I shown over here for convergence of series. These anticipate ideas of calculus. Concepts of differentiation. The idea of instantaneous change in trigonometric functions. Bhaskara, he did that. Just like today in high school, we say maximization of function, minimization of function, take the d by dt of the function, set it equal to 0, you get the maximum or the minimum turning point of the function. That's what we do in high school, right? Bhaskara was the one who did that. He said that at the maximum point, this rate of change is 0 for a particular function for the sin x and things like that. Second, geometric and arithmetic summation, very similar to integration, integral calculus, to approximate the area under the curve. We are seeing these things in Yukti Bhasha. We are seeing recursion in generating series, solving problems. These are all foundational to iterative methods and calculus. So calculus itself we are seeing in ancient India. Geometry, I talked to you at length about that earlier, Sulba Sutra, practical geometry for altars, right angle triangles, and other such things. For example, this right angle triple is seen over here. Diagonal of a rectangle produces both the area which the two sides produce separately. It is equivalent to a square plus b square equal to c square. And geometric construction, squaring the rectangle or circle, constructing a square equal in area to a circle. This is not easy, by the way. If I give you a circle and ask you to construct a square equal in area, that is simply non-trivial. But Indians had constructions to do that. Converting a square into a circle, the inverse process. So all these things were done by ancient Indians. The value of pi, I started out this talk today saying pi connects us in the arc of time from 5,000 years ago to Ramanujam, right? Every Indian mathematician of repute has used pi and approximations for pi. So Aryabhatta used this value. Madhava had 11 decimal places he used in his infinite series, right? So in Sulba Sutra, Baudhaya used 3.125. It has got 0.5% error. Jain scholars use root of 10. This is about 0.6% error. Aryabhatta is very accurate. Madhava, as much accuracy as you want, you can use it. Ramanujam, infinite series, which converges very, very fast. And you might also wonder, what did Indians call pi? Did they call it pi? No. There were different terms, right? Some people called it asanna. Some people called it vritti paridhi bhaga and other such names. There are different names. Approximate, meaning approximate part ratio of circumference, relationship between circumference and diameter, shadow, for example, chaya in trigonometry, and portion of the circle. So different people in different contexts use different phrases for pi. There's no one uniform word for pi, but we know why this is used and the values people used. Come to the end of the talk over here, logic, right? Logic forms the basis of all of our computer science. You cannot do any algorithm computation. In other words, a modern world would collapse if we didn't have logic. Where did this logic come from? Earliest rigorous logic, I opened it out with that, right? The darshanas, Samkhya, Nyaya, Vaisheshika, Mimamsa, they all use structured logic for deductive reasoning. So whether you see the Vedas, the Upanishads, they have discussions, they have paradoxes, negations. I have not put a timeline on this because it is greatly in dispute and you'll disbelieve me if I give you some timelines over here. Not yet, later on I will propose that. In the Jain works, relativistic logic, sevenfold predication, just like we got binary logic with 2 or three-valued logic with the Z state or the X state or four-valued logic with the 0, 1, X and Z. They had sevenfold predication to find it BC onwards. Buddhists, Dignaga. Dignaga, by the way, was a southern Indian man, a Buddhist monk who went to China and formed a certain school over there and a philosophy. So he worked in epistemic logic, inference theory and such things. Rishi Gautama, with Nyaya, he had his logical categories and so on. So if you look at the difference between Indian logic and Aristotelian logic, we are seeing 5 form, whereas here's 3 form. Epistemology strongly integrated in the Indian way of thinking in all of Indian knowledge systems. Every knowledge system, we see the impact of Indian logic over there. In Aristotelian logic, it is not at all used, very little emphasized in the day-to-day life as such. Relativity, basically, it is embraced by Jains, Buddhists. I don't think much more than that. Aristotelian is binary, absolute. The language, semantic, linguistic depth is a formal structure over here. Evolution is extended into modern symbolic logic. We can see that. I've shown to you today hints of all of these things all over the place. And Aristotelian logic is the basis of classical Western logic, whereas Indian logic is more applied and used even today. So the applications of math is something I will do in the next episode. But just to give you an overview, it is applied in Vedic rituals, geometry, area formulas, transformation, astronomy, trigonometry, sine tables, interpolation, architecture, geometry, ratios, symmetry, commerce. We saw all these things, algebra, arithmetic, decimals, governance, measurements, algebra, arithmetic, in medicine, time cycles, arithmetic ratio, education, combinatorics, philosophy, zero, infinity. So India never secularized mathematics saying, I'll study it for the sake of mathematics. It was deeply embedded in our day-to-day lives, in everybody's day-to-day lives. That is what I've shown to you in today's episode. So with that, we come to the last slide over here. What I've done, I hope I took you through an amazing journey through time from many, many thousands of years ago till medieval times. So we have examined the unparalleled, no other civilization, not the Egyptians, not the Babylonians, not the Chinese, not the Greeks, not the Romans, not the Arabic people, the Muslim civilizations, not the British. Nobody until much later periods were anything near Indians in mathematics, unparalleled contributions. You might be surprised because nothing like this is acknowledged in Western histories of mathematics because they are deeply Eurocentric. Mathematics was the pride of the Western civilization after the so-called Renaissance and after the so-called age of reason and the scientific revolution. Mathematics was seen as something uniquely appearing in the Western civilization, which the natives, the Africans, nobody had, only they had. So India had to be de-emphasized. That is why Bakshali manuscript was disordered and given to Rudolf Hormann, so that he couldn't even do the right thing in it. Because many Eurocentric scholars were there in that period of time, trying to show the superiority of Greek, of mathematics and so on. Anyway, this is a long story. We will address this in a much later episode when I'll talk to you about the impact of Indian knowledge systems on the world. So in the next month, I hope to talk about exploring applications of math. So we're going now to Q&A, and I think our hosts want you to write your questions in the chat and they will read it out to me. So like I said here, nothing is trivial or silly. So go ahead and ask, but I warn you, none of my answers are trivial. It might go very deep. And if my talk intrigues you today on some of the things I've been asserting but not telling you why, please do see some of my talks for context. I've shown some of my talks, many of them are on YouTube, and you'll get some context, what I'm talking about with evidence on some of these things. All right, you can find me on YouTube by searching for my name. You can reach out to me here or follow me on Twitter or X or on Facebook. With that, I'll stop sharing. Thank you.
Thank you so much, Dr. Vedam. I indeed had goosebumps while listening to this, so I'm sure many others did. The chat was super active, and I think so many people were very interested in the things that you were connecting. We do have a few questions, and I know we're already over time, so we can answer as many as we can, and then maybe you can answer the rest offline or at the start of the next episode. But just starting at the top of the chat, what we got early on from Girish was, with all this supporting information about like India, the ancient India and how it connects to engineering, how can we get the credit passed on to the deserving individuals and reverse the falsification?
It's a very good question. Thanks for that, Girish. So the process has started. So some of the pioneers in this field for reversing this were people like Tilak, Lokmanya Tilak. I gave a couple of names, Iyengar, Datta in the 1930s, and so on, going on to Kota Venkatachalam in the 1950s, going on to people like K.M. Munshi, going on to many other scholars who are passed on now, including our present-day scholars. There's a lull in the revival of Indian systems thanks to the socialist education system we had from 1947 till 2014. But there has now been a revival in the Indian thinking. In the 90s, we had scholars like Subhash Kak, we had scholars like David Frawley and others who were trying to do research on astronomy, things in mathematics and so on. But now we are seeing many more people. C.K. Raju, who did some pioneering work in history of mathematics, impact on other civilizations. Then from 2012, I myself have been giving talks, right? Many talks, public talks on these areas. And I'm glad to say that when I started, there was almost zero knowledge about these areas and almost nobody talking about these. But over the years, I've seen more and more people have started. It's like a tsunami now, growing tsunami rather, and more and more people are jumping on the bandwagon now. So I think what should happen is we as parents and as elders in the society and others, and you as professionals and so on, need to internalize this. See my talks, see talks by other thought leaders, read their books, and try to internalize this, teach your children, teach the next generation, write blog articles, popularize it, so more and more people become aware of this. And eventually change will come through NCRT, through textbooks. Once NCRT changes its textbooks, we can hope that US textbooks can also be changed. Today it will not, because they'll say in India itself they're teaching these kind of nonsense, whether it's in California or Texas. Change will come. It'll take a little bit of time, but it'll come. But we need to be on a quest for truth over here. Okay.
That's great. Yeah. Mahesh asked, please share history of fast Fourier transform / discrete Fourier transform and any links to ancient India.
Excellent question. Excellent question. You have anticipated what I might do in the next seminar, next episode over here. I'm going to talk about starting with the sine function, how we started the sine, went on to a Taylor series kind of sine approximation going on to that, and how that went to the West and became the Fourier series, and how from Fourier series it went to the Fourier transforms, how the transforms came, and from transforms how it went into the later on the fast Fourier transform computationally, the discrete transform, the Laplace transform. I will try to address these things, including today if we don't have the cosine transform, we can't even do what we're doing now. Any kind of video transmission or audio transmission digitally is happening because of compressions like the discrete cosine transform. Where did that come from? These are all offshoots of this ancient thing. So we can trace it back in time to a very ancient contributions of our ancestors. Cumulatively, they have led to where we are today. So I'll trace all these developments in future episodes.
Very exciting. Looking forward to it, as many people are, I'm sure. Venkat asks, in large language models, AI/ML models, there are concepts like training data, inference, weights and measures, etc. used. Do these concepts take root in any of the concepts discussed in this session today? It looked like that, but wanted some additional explanation and confirmation if there is.
We had the original learning mechanism over here, Venkat. We had the guru who would state a verse and the students would recite them over and over again till the brain neurons come and make those weights and connections, synapses, and then we get the knowledge. So we had the original learnings, if you will. Pardon my trivial answer, but that's what we had, right? We had a learning system that was oral as well as written, both. And we had a scholarly tradition through gurukulams where people would learn and do all of these things. So LLMs and artificial neural net and all these things are recent innovations after we have got the computer, digital computer, after we had the perceptron of the 1950s and 60s. That has led to the artificial neural nets, that has led to all these CNNs and convolutional neural nets and whatnot and these kind of things today. So I think the bottom line is no, I don't think we had networks of this form, but the algebra and the semantics can be seen in abstract works by Panini and others. We do see those kinds of algebras coming over there. In a sense, a neural net is doing functional approximation. If I can do a polynomial approximation, in Western math, we have the Stone-Weierstrass theorem. If you look at the Stone-Weierstrass theorem, that gives us the foundational basis for functional approximation, a polynomial functional approximation. So those kind of mathematics was known to our ancestors. Aryabhata's Kutuka algorithm, for example, does there even exist an answer? Before he starts Kutuka algorithm, does it exist an answer? Those kind of existential questions, those kind of approximations and such things, yes, the roots of that go back to Indian mathematics. That inspiration has led later scientists to do many, many other things today.
Sushil asked, did Panini establish the programming language syntax later used in Algol and which later got named BNF?
Okay, the BNF form, the CNF and the BNF forms. Yes, all these things, I alluded to some of these things. I alluded to how the symbolic representation that Indians had that could be expressed. For example, the propositional logic of Panini, using the sutras that he had, they could be expressed in all kinds of trees, algebraic trees and those kinds of things. So the structure that is found in the Paninian works, yes, it did inspire programming structures. I cannot tell you offhand which programming language was based with the Algol or earlier ones. I don't remember, so I'll have to look it up and tell you. But yes, it did inspire. And there are people even today who claim that the kind of inferences we can make with Paninian grammar makes it suitable for a lot of reasoning, let us say, automated reasoning. But today we have a tendency to have gone into AI, right? Everybody's using AI. For example, we have now LLMs that are even capable of trying to get the syntax, the sentiment, the lemmings, and other such things that we say, the stem, lemmings, all these kind of things. They're able to get the sentiment, they're able to do all these kinds of things. So we are able to do with larger and larger networks, we are able to do little more, and so on. But yes, the roots of these things go back to pretty ancient times.
Thank you so much. I know that we're over time, so I'm going to take the rest of the questions and I'll keep them for next episode so that more people will come back and listen. Thank you so much, Dr. Vedam. This has been eye-opening. I don't know if you've gotten a chance to look at the chat, but everyone has really found this a really incredible episode, and I think we're all looking forward to more. Very excited for the future episodes that we have. I really appreciate you taking this time out of your day to come and talk to us. So please, everyone, come back for next month. I will send out an email for that with the new Zoom link and things like that. And really looking forward to it. And feel free, please, to join ASEI for those non-members in this chat today. Thank you so much, Dr. Vedam.
Thank you. Thank you for inviting me, and namaskar to everybody. Hope to see you all the next episode.
Thank you.
Thank you.